Looking toward the Milky Way's bulge, the bright red star is Antares, which is the heart of Scorpio. That little brown blotch is the galactic center, home to the supermassive black hole Sagittarius A. And that bright spot is Messier 20, also known as the Trifid Nebula. And it's insanely numinous because it's a combination dark nebula and reflective nebula. And if we come to the corner of it, we can go to this seemingly dark, hollow area of the sky where it looks like there's not very much going on. And if we zoom in 47 light years, we can see more darkness. That's actually the location of W1935. And last decade, it was identified as a brown dwarf candidate by NASA citizen scientist Dan Castleton. He used a machine learning algorithm to find it in the data from NASA's Wide Field Infrared Survey Explorer. And in 2019, it was verified by a team of astronomers and astrophysicists using data from the European Space Agency's Gaia probe. Finally, the Spitzer Space Telescope was pointed at it a couple of times and generated these images. All this may not sound like much to go on, but it was enough to make initial estimates of its temperature, mass, and age. In 2023, just a few months ago, another group of astronomers pointed the James Webb Telescope toward a dozen brown dwarfs, including W1935. They got information on their spectra and movements. And hidden among the data was this: an unexplained blip in W1935's methane spectrum, indicating emissions of infrared light rather than just absorption. I want to talk about W1935 and these light emissions, which are believed to be auroras, and how they might be powered. Along the way, we're going to talk about brown dwarfs in general, how they were theorized, what powers their early lives, and how they degenerate. Then we're going to touch on the auroras in our solar system, and a few ways the ones on Jupiter are different from what we see on Earth. And hopefully, these things can give us some insight into the beautiful mystery that's just been uncovered. So let's get into it. I'm Cameron and this is my channel. Welcome to the Sexy Universe. In 1962, University of Virginia astronomer Shiv S. Kumar published this abstract in Astronomical Journal, where he described his theoretical work on the objects that would later be known as brown dwarfs. They're much heavier than gas giant planets like Jupiter and Saturn, and in fact, the minimum weight is believed to be 13.7 times the mass of Jupiter. The heavier a planet is, the more gravity it generates. They hold their size and shape because equilibrium is reached between the force of gravity and the Coulomb forces between their atoms and molecules. Atoms contain a nucleus, and that nucleus is surrounded by an electron cloud. And since electrons all have a negative charge, the electron clouds between the atoms naturally repel each other. This is called Coulomb pressure, and it limits how close to each other the atoms can get. Therefore, it limits how dense a planet can get. But if a planet were to accumulate more and more material, there would eventually be enough gravity to overcome the Coulomb pressure, and the atoms would pack together in the core with virtually no space between them. With the electron clouds pressing against each other, the size of the object would be determined by how well the electron clouds could hold up and maintain distance from their atomic nuclei. This is called degeneracy pressure, and it sets the size limits for both brown dwarfs and white dwarfs. The dynamics get a little bit strange in this area, where degeneracy pressure is more important, because when material falls into these objects, it increases their gravity. This presses all of the individual atoms smaller, so the object itself gets heavier, but it doesn't get any bigger. And in the case of white dwarfs, getting heavier actually causes them to shrink. So what about stars? They all have masses greater than brown dwarfs, but they also take up a lot more space. So why is that going on? It's because when the pressure and temperature get high enough, nuclear fission starts, and it creates enough heat to overcome gravity and push out all the layers. A similar dynamic also happens with brown dwarfs, but only early in their lives. If a brown dwarf is heavy enough, it'll generate enough pressure and heat to start deuterium fusion in its core. Ordinary hydrogen atoms consist of only one proton and one electron, but deuterium has a neutron as well. The neutron allows it to merge with another hydrogen atom and form helium-3. In a fully developed star, that helium-3 would undergo a couple more steps and become helium-4. But in a brown dwarf, this doesn't take place. Helium-3 is stable on its own, so it accumulates in the brown dwarf's atmosphere. Deuterium fusion heats the core to around 2 million degrees Fahrenheit. During this fusion phase, they have an estimated surface temperature somewhere between 4,500 and 5,000 degrees Fahrenheit. Most of their electromagnetic emissions are in the radio and infrared bands, but some can put out X-rays as well. Only about 15 in every 100,000 hydrogen atoms is deuterium, so the fuel supply for all this is very limited. And even though convection currents in the brown dwarf eventually churn all the deuterium into the core, there's still only enough to maintain fusion for around 10 million years. And that's only 1,000th of the lifetime of a star like our Sun. After the deuterium is exhausted, the brown dwarf slowly cools and shrinks back down. For an object to become a full-fledged star, it has to have enough mass to fuse not only deuterium, but light hydrogen as well. And this puts a line between the mass of brown dwarfs and the smallest stars. That line is at about 80 Jupiter masses. After the fusion phase is over, brown dwarfs slowly cool over billions of years, until they get as cold as empty space. As they cool down, metallic clouds of silicon, iron, and other elements form, and eventually they drift down to the core. At the same time, molecules like ammonia, water, methane, and carbon monoxide and dioxide start to form and accumulate in their atmospheres. So even as they lose heat, brown dwarfs are still vibrant, complex objects. There were many attempts to search for brown dwarfs beginning in the 1980s, but the first one was found in 1994 by Rafael Lopez, Maria Zapatero Osorio, and Eduardo Martin. They used the 80-centimeter telescope at the Teide Observatory in the Canary Islands, and they named their discovery Teide 1. Teide 1 is located in the Pleiades cluster, about 430 light-years from Earth, and its surface temperature is around 4,200 degrees Fahrenheit. It's about as heavy as 55 Jupiters, and it's estimated to be somewhere between 70 and 140 million years old. In order to verify it was a brown dwarf, the astronomers used the 10-meter telescope at the Keck Observatory in Mauna Kea. And they did this by searching for its lithium signature. When a star is born, any lithium in it is destroyed pretty quickly by proton bombardment. But brown dwarfs don't get hot enough for that. So a good way to identify them is by looking for lithium in their spectrum. And in Teide 1, they found exactly that. So Teide 1 is young, large, hot, and it has this orange-magenta color. It's also part of a dynamic star cluster, the Pleiades. By contrast, W1935 is small, cold, dark, and ancient, and it's out there floating through the galaxy all on its own. And here are its stats with Teide 1's for comparison. W1935 is 47 light-years from Earth in the constellation Sagittarius. The newest estimates put its weight somewhere between 6 and 35 Jupiter masses. Its temperature is around 415 degrees Fahrenheit, and its age is somewhere between 1.5 and 6.5 billion years. We know Teide 1 was born in the Pleiades cluster, but we have no idea where W1935 came from. A group of citizen scientists with NASA's Backyards World project recently pointed the James Webb Telescope at W1935 and a few other brown dwarfs to gather information on their spectra. And in a second, I'm going to cut to Jackie Faraday's presentation on their discovery. For a little bit of background, she's an astrophysicist and senior scientist at the American Museum of Natural History in New York. She's also a co-founder of the Backyard Worlds project. If I could just cut and paste her presentation, I would, because she explains it better than I can. But I have to break in a couple times to stay within fair use, so please be patient when I do that. Let's hear what she has to say. Earlier in her section of the press conference, Dr. Faraday talked about W1935 and the group of brown dwarf objects that they looked at. And now she's about to talk about W2220 and then compare the two.
This other object, 2220, was discovered by NASA's WISE team several years before 1935. But I'm going to show you the two of these together because they're very similar to each other. They're spitting distance away, within 50 light years, both of them. Their temperatures are about 400 degrees Fahrenheit, which is like what you bake your cookies at. And their masses are between 6 and maybe 35 times the mass of Jupiter. So they're very akin to Jupiter. We focused on JWST near-spec data because we wanted high-resolution look at the atmosphere so we could really tell what was happening in the atmospheres of these objects. So now I'm going to show you the spectra. Here is our JWST near-spec spectra of these two objects. What you're seeing is a spectrum sculpted by intriguing chemistry. Every wiggle that you see in here is real. A real molecule that's absorbing light. It's real information on what may be happening in these atmospheres. It's got cloud information in it. It's got information about anything that's happening in the atmosphere. Now, compare and contrast. I told you these things have very similar temperatures. So one of the most intriguing thing we found when we looked at our full sample was how similar these two objects looked to each other.
And I'm just going to point out what we're looking at here is the infrared spectra. The JWST actually has an extremely good infrared camera. And as you can see with this little chart, we're down close to the near infrared spectrum around the middle.
We put them up on each other. You can see their wiggles are matching each other, right? It's great. But there is something different between the two of them. As I'm talking and pointing out some of the molecules, see if you can identify it. Because it was like a pebble in a shoe I couldn't get rid of. I was only focused on this one feature in the blue object called 1935. So starting on the right-hand side, just to give you an idea of what's sculpting, what's shaping these beautiful spectra, water and ammonia are out here at the longer portion of the wavelength. Water and ammonia are out here. Move a little bit farther to the left, carbon monoxide. There's a lot of intriguing carbon chemistry in these objects. Carbon chemistry make that beautiful shape that you're seeing. And then carbon dioxide, there's more of it than we expected. The whole different press briefing I can give you on what we saw in the carbon chemistry. I'm going to talk to you about what comes next, which is that big chunk to the left here. It's methane that's shaping everything that's kind of shortward of 4 microns here. The methane it's a popular molecule. It absorbs a lot, and we knew it was there. It's why these objects are so faint out here, because methane is absorbing a lot of light, right? But if you see with one of the arrows is pointing to here, there's a bump. So our team was left to try and figure out what this bump was. So I'll zoom in to show it to you. No other object in our sample had it, spoiler, just this object, 1935. Now at first we said, okay, here's what we're gonna do. We're gonna go through and look at every single dither. Maybe it's an instrument thing, wasn't an instrument thing. Then we turn to the modelers and we say, guys, let's look at the models. It's in the grids, what's with the bump? Because we did not think to go to what is now very obvious to us. Instead of the methane in absorption, which is what 22 is doing, it's methane in emission. But why is methane in emission in an object that's the temperature that you cook your cookies at, and also 50 light years away without a host star?
So as she pointed out, this looks like methane in emission in W1935. Just to give an idea of what temperature we would expect to find methane in emission at, I went ahead and looked up this paper. It's from 2008, but I'm not sure that matters too much for the kind of work they were doing. And what these researchers were able to do was collect emission spectra of methane. This temperature range they looked at goes from 1800 Fahrenheit to 2800 Fahrenheit, or 1000 to 1800 degrees Kelvin. And that's the temperature they had to get to in order to get an infrared radiation spectrum from it. So to have this object in outer space at 415 degrees emitting this kind of spectral light begs us to find some explanation for it.
Well, we turned to the solar system to help us explain what was going on. So here's images of Jupiter. On the left is the Hubble image in optical with the ultraviolet overlaid on it. And then on the right is the JWST image of Jupiter. And you can see very obviously on here at the poles, it has an aurora. And what we saw right away is that Jupiter had methane in emission. Jupiter had the bump. So we had a great explanation. Okay, perfect. Because then the other question is, why does Jupiter have an aurora going off? Well, it has a sun. It has the star. Our object does not have a sun, but what we discovered in trying to figure out what the relationship that Jupiter has with its methane emission is it has a second contribution, and that is from the active moon Io. That does not mean that we're declaring that we have found an active moon, but it's one of the explanations that can help us figure out why this methane is in emission.
So I'm going to cut out from this press conference right here, but I'm going to put a link to it in the description so you can look at the whole press conference if you want to. Since Dr. Faraday talked about auroras on Jupiter and how there might be something similar going on W1935, we can start there. Auroras in our solar system need a few ingredients. First, the solar wind, which is radiation from the sun. Second, a magnetic field. And last, an atmosphere. On Earth, some of the solar wind enters the upper atmosphere where the planet's magnetic field lines meet at the winter pole. The radiation strips electrons off some of the atoms in the upper atmosphere, and the charged particles start interacting with the rest of the air, creating these curtains of light. This is a picture of the southern lights from space. And as you can see, there's basically one large circular band. And while there are places where it's brighter and others where it's spread out, it's fairly uniform. It's also confined within an inner and outer bound around the southern magnetic pole. And the auroras only show up around one pole at a time. So now let's look at auroras on Jupiter. This image is from the Chandra telescope, so it's Jupiter's auroras in the X-ray spectrum. You can see there are auroras at both poles at once. Jupiter's axis is only tilted an eighth as much as the Earth's, so there's solar contribution on both sides. You can also see that the auroras at the North Pole extend further down and are more variable than the auroras on Earth. This ultraviolet image from above Jupiter's North Pole was captured by the Juno spacecraft. You can see there's an inner loop and several partial rings in the outer loop. The primary contributor to auroras in the inner loop is the solar wind. But the primary contributor to the outer loop is Jupiter's moon Io, with smaller contributions from the moons Europa and Ganymede. These three moons orbit close enough to Jupiter that the planet's immense gravity morphs the mantle between their crusts and sets off volcanic activity. This is particularly true on Io, whose surface is punctuated by hundreds of volcanoes that constantly spew sulfur dioxide into space, creating a trail of plasma in the moon's wake. The particles are drawn by Jupiter's magnetosphere toward the poles, where the plasma injects itself into Jupiter's atmosphere. It ignites an aurora where it enters. The entrance spot remains stable, but Jupiter's rotation causes it to draw a loop. Europa and Ganymede make similar contributions, though not as big as Io's. And it's because these two moons are more distant, so they're not subject to the same magnitude of gravitational distortion. Instead of volcanoes, they have large, powerful geysers producing plumes of water. Those water molecules are also ionized and follow the magnetic field to Jupiter's poles. Here you can see Jupiter's outer auroral loop with contributions from Io, Ganymede, and Europa all labeled on it. So if Jupiter's moons can create this much aurora, then it's not hard to see how a moon orbiting W1935 could do the same thing. And that's why it's the #1 suspected cause of the light emissions. But there are a few other possibilities I'd just like to highlight very quickly. First, lightning. We know it exists on all the giant planets and is produced by ammonia clouds, which W1935 has in abundance. If W1935 is subject to continual lightning storms, this is a possibility. Volcanic activity from settling in the Brown Dwarf's core. Active volcanism beneath the atmosphere could push plasma jets into the upper atmosphere, igniting an aurora. An X-ray source that's routinely directed toward the brown dwarf, such as an emission jet from a distant black hole or neutron star. Now, all of these possibilities have problems that make them unlikely. For example, an emission jet would produce a stream of plasma that should be detectable from Earth. And lightning just doesn't consistently produce as much light in our solar system as auroras do. But imagining possibilities and testing hypotheses is part of the adventure of science. Another interesting facet of this discovery is that W1935's atmosphere has carbon monoxide in abundance. Because the carbon on this molecule has a couple free electrons, it's a precursor to lots of complex carbon molecules. And in the presence of lightning and plasma, there are many different organic molecules that could be created there, including things like proteins and fatty acids. This is a truly beautiful discovery, and when new observations are made that help us solve the mystery of W1935's auroras, I hope you and I will be here to talk about it. Once again, we have show notes with references and cool graphics. They'll be posted on my website, thesexyuniverse.com, and I'll put links to them and the AAS press conference in the description. I believe the ideal life is a nonstop process of learning and growing. Thanks for learning and growing with me. As always, I want to hear what you think, so please put your thoughts and information you'd like to share in the comments section below, and hit the like and subscribe buttons on your way out. Stay on your game, and I'll see you next time on The Sexy Universe.